Welcome everyone in the lecture series of nuclear magnetic resonance spectroscopy. In this video, we are going to see designation of nuclei in spin system, that is Pople nomenclature system. In the molecule, there are different types of proton and they are designated as A, B, C, D or A, M, X, etc. by using the rules given by Pople nomenclature system. Let us study designation of nuclei in spin system. First we see what is meant by a spin system. The group of coupled protons is termed as a spin system. A spin system is present within the molecule. For example, isopropyl propionate. This is the structure of isopropyl propionate. In that case, there are two types of spin systems are seen. This is isopropyl group which is of 7 protons, and that methyl group proton and methane group proton couple with each other, and it is of 7 spin system. Similarly, this ethyl group of propionate group, it exhibits the 5 spin system. Methylene and methyl group protons are coupled with each other. But coupling between these 5 spin system and 7 spin system is not possible, as there is a difference of 5 covalent bond. That is, coupling between these two spin system is not possible, but within the spin system the coupling is possible, and that is a group of coupled protons. That system is known as a spin system. Let us study the nomenclature. A simple nomenclature system, that is Pople nomenclature, is used to designate spin system which is based on a relative chemical shift position from each other. Letters of alphabet, that is A, B, C, D, etc. are used to designate group of protons. Let us study some rules. Rule 1. A group of protons which are strongly coupled and their chemical shift difference is comparable to coupling constant are denoted as A, B, C, etc. If that letters consistently comes, then there is a small chemical shift difference, and that letters are given in order of increasing shielding. That is, highly deshielded proton is designated as A, then B, then C, etc. For example, ABC denotes a strongly coupled 3-spin system. For example, 2,5-dichloronitrobenzene. In that case, there are 3 sets of protons, A, B, and C. That A proton is highly deshielded, therefore it is designated as A, then B, and then C. And the chemical shift values of these 3 type of protons are nearer, therefore they are designated as A, B, C, etc. Then rule second. A group of protons which are weakly coupled and their chemical shift difference is large in compared to coupling constant are denoted as AMX, etc. For example, the spin system ABX indicates protons A and B are strongly coupled and their chemical shift values are nearer, and both protons are weakly coupled with proton X. The X have the chemical shift value far away from A and B. The spin system AMX indicates protons AMX are weakly coupled to each other and their chemical shift values are well separated. For example, furan 2 aldehyde. In the ring protons, that is AMX, and the chemical shift value of these 3 protons, 3 type of protons, is far away from each other, therefore the letter A, M and X are used. Then rule number 3. The number of magnetically equivalent protons in each group is denoted by a subscript. For example, ethyl group in ethyl acetate. That ethyl group, in that ethyl group there are 2 spin systems. Deshielded proton is designated as A, less deshielded is X3. In case of CH2, there are 2 protons, therefore it is X2. In methyl group, there are 3 equivalent protons, therefore it is X3. Therefore, ethyl group in this compound exhibited or designated as A2X3 system. Chemical shift value A and AX is well separated. Another group, ethyl group in N-hexyl bromide. In that case, chemical shift value of CH2 and CH3 are very close to each other, and for CH2 there are 2 protons, therefore it is designated as A2. There are 3 protons, therefore it is designated as B3. That is 3 indicates there are 3 protons, 2 indicate there are 2 protons in that spin system. Thus ethyl group is designated as A2 and A2B3 system. That is, number of protons are denoted by a subscript. Then the fourth rule is the primed symbols are used to designate chemically equivalent but magnetically non-equivalent protons. For example, 1,3-butadiene. In that case, there are 3 sets of protons. As that there is a symmetry between the molecule, A and A dash are chemically equivalent but magnetically non-equivalent because coupling of HA with HB and HA dash with HB is not same. Similarly, proton B and B dash, C and C dash are chemically equivalent but magnetically non-equivalent. They have same value of chemical shift but a different coupling constant. And for such type of protons, primed symbols are used. Let us study different type of spin systems. First we see system containing 2 interacting nuclei. That is, spin systems are of the type A2, AX and AB system. A2 system. A system containing 2 magnetically equivalent protons. They always give singlet in the spectra. As they are equivalent protons, the coupling is not possible and they give the singlet in the spectra. For example, 1122 tetrachloroethene. These 2 protons are chemically and magnetically equivalent. That is, CH2 group. Another type is that in general, protons of methylene group, that is CH2 group, having absence of protons on adjacent carbon atom also shows A2 system. Then next type is AX system, a system containing 2 weakly coupled protons having wide difference in chemical shift values. These are the 2 proton system, but chemical shift value of A and AX there is a wide difference. And as they couple with each other, A gives the doublet and AX also gives the doublet in the spectra. These doublets have the equal intensity. The spectra is first order spectra. For example, dichloroacetaldehyde, A and AX. A gives doublet, X also gives doublet in the spectra. According the splitting is due to N+1 rule. Then AB system, a system containing 2 strongly coupled protons having nearer chemical shift value. Signal of A and B are distorted and not symmetrical in spectra. In that case, A coupled with B, it gives doublet. B coupled with A, it gives doublet, but signals are not symmetric. The intensities of doublet are not symmetric. In case of AB system, the coupling constant can be calculated like this. J of AB is equal to nu1 minus nu2, that is equal to nu3 minus nu4. That is the distance between 2 multiplates or lines between multiplate, that is nu1 minus nu2 or nu3 minus nu4. And the chemical shift difference is calculated by using the equation delta nu is equal to square root of nu4 minus nu4, nu1 minus nu4 into nu2 minus nu3. And intensities of multiplates are in the ratio I3 divided by I4 is equal to I2 upon I1, that is equal to nu1 minus nu4 divided by nu2 minus nu3. This is the example of AB system. 3-bromo 2 tertiary butoxythiophene. In that case, these two protons are non-equivalent, but chemical shift values are very nearer to each other and they exhibit AB system. Then we see system containing three interacting nuclei. The systems are like this: A3, AX2 or A2X, AMX system, ABX system, ABC system, AB2 or A2B system. First we see A3 system, a system containing three magnetically equivalent protons, and they always give singlet in the spectra. For example, methyl iodide, in case of methyl iodide, it exhibits A3 system, only one type of proton. In case of 1,1 trichloroethane, 1,1,1 trichloroethane, it exhibits also A3 system. All these three protons are chemically and magnetically equivalent. In case of paraxylene, there are two A3 systems. These methyl group protons, they have same chemical shift value and they exhibit two A3 system. That is, A3 system always gives singlet in the spectrum. Then next type is AX2 or A2X system, a system containing two magnetically equivalent protons coupled with third proton which is far removed in chemical shift. And two signals, in case of AX2, A gives triplet and AX gives doublet in the spectra. For example, 1,1,2 trichloroethane, and it exhibits AX2 system. A is designated for highly deshielded proton. A gives the triplet while that X proton gives the doublet in the spectra according to n+1 rule. And in that case, J of AX is exactly same in both multiplets. This is AX2 system or A2X system. The next type is AMX system, a system containing three non-equivalent protons having wide difference in chemical shift values and having three different values of coupling constant. J of AM is not equal to J of AMX, which is not equal to J of AX. And three double doublets are seen in the spectra, that is, total 12 lines are seen in the spectra. For example, vinyl acetate. In case of vinyl acetate, there are three set of protons A, M and X. The A proton couple with X, we get the doublet. Again A proton couple with M, and each line of doublet again splitted into two lines. Therefore, we get the double doublet in the spectra. That is, first A couple with X, we get doublet. Then again it couples with M. Therefore, each line of doublet again split into two lines, and such type of double doublet is seen in the spectra. Similarly, for proton X and proton M also, we get double doublet in the spectra. And thus, in case of AMX system, the spectra looks like first order, but it is a non-first order spectra. And total 12 lines are seen in the spectra, and coupling constant J of AM, J of AX and J of MX are totally different. Then next system is ABX system, a system containing three non-equivalent protons, but two protons have comparable chemical shift values. That is AB, these two protons have comparable chemical shift value and coupled with third proton having well removed in chemical shift. That is coupled with proton X, which have different value of chemical shift. In this case also, total 12 lines are seen in the spectra. Three double doublets are seen in the spectra, but the AB portion may be overlap with each other. That AB portion, as their chemical shift values are nearer, they are very close to each other. Sometimes overlapping of signal may take place. For example, 2,3-dichloropyridine. That is the designation proton A, proton X and proton B. ABX system. Then next, ABC system. A system containing three non-equivalent protons, but these protons have nearer chemical shift values. The spectrum is complex in nature. In that case also, the coupling between these three protons similar to AMX, but as their chemical shift values are very close to each other, the, the overlapping of signal takes place, the crowding of signal takes place, and the spectra looks like a complex spectra, and it is difficult to resolve. Generally, trisubstituted benzene shows ABC system. For example, 3-nitroarthoxylene, this is a ABC system. 2,4-dinitrochlorobenzene, this is also ABC system. 3-nitrosalicylic acid, this is also ABC system. That is, in case of ABC, these protons are strongly coupled with each other, but their chemical shift values are very close to each other. Therefore, the signals are sometimes overlap and complex pattern is seen in the spectra. Then next type is AB2 or A2B systems. A system containing two magnetically equivalent protons coupled with third protons which is not far removed in chemical shift. That is, their chemical shift values are very nearer to each other and the spectrum is more complex in nature. And we cannot identify a particular signal in the spectra. For example, 2,6-lutein, in this is a ABC system, chemical shift values are very close to each other. Therefore, the spectrum is complex in nature. It is a second order spectrum. Then we see system containing four interacting nuclei. The some systems are A2X2, A2B2, AA-XX- and AA-BB- AMPX systems. First we see A2X2 system. A system containing two sets of protons in which two magnetically equivalent protons coupled with other set of two equivalent protons which is far removed in chemical shift. That is A2 protons. They are these two equivalent protons coupled with this X2 type of equivalent protons, but their chemical shift difference is wide. And in that case, both type of proton gives triplet in the spectra. For example, this compound, in this case, this is a A2X2 system. For A and X, we get the triplet in the spectra. The spectra is first order spectra. Delta nu by J is greater than 10. The another system, A2B2 system. A system containing two set of protons in which two magnetically equivalent protons coupled with other set of two equivalent protons having nearer chemical shift values. That is A2 protons coupled with B2 proton having nearer chemical shift values. And both type of protons gives triplet in the spectra. But as their chemical shift values are very close to each other, sometimes overlapping of signal may take place. Generally, compound containing CH2 bearing substituents of similar electronegativity on both sides shows A2B2 system. For example, 2-chloroethanol. And as the electronegativity of chlorine and oxygen is nearly same, therefore it exhibits A2B2 system. But that CH2 proton and that CH2 protons are not equivalent. Therefore, they exhibit A2B2 system, A portion and B portion close to each other. Delta nu by J is less than 6 and the spectra is second order. Next system, AA-XX- or AA-BB- system. A system containing two sets of protons which are chemically equivalent but magnetically non-equivalent. Signals are not symmetric and complex pattern is seen in the spectra. For example, AA- and BB- system. This is 1,2-dichlorobenzene and in that case it exhibits AA-BB- system. That is, A and A- are the chemically equivalent protons but magnetically non-equivalent, as coupling of A with HA with HB and HA dash with HB is not same. This is the orthocoupling, this is the metacoupling. Therefore, although they are chemically equivalent, they are magnetically non-equivalent. Similarly, B and B dash, they are also chemically equivalent but magnetically non-equivalent. And therefore, although their chemical shift values are same, the coupling is different, and such type of complex spectrum is seen in the spectra. This is the example of AA-XX system. AA- protons are chemically equivalent but magnetically non-equivalent. Fluorine is magnetic nuclear, therefore coupling of HA with FX and HA with Fx dash is different. And such type of complex pattern is seen in the spectra, and the spectrum is non-first order or second order. Then next system is AMPX system. As the letter denotes AMPX, that is there are four type of protons, four set of protons, but their chemical shift values are wide difference or different in nature. For example, such type of systems are seen in ortho and meta disubstituted benzenes and in 2,3 substituted pyridines. For example, 2-chloro-nitrobenzene. In case of 2-chloro-nitrobenzene, there are four set of protons. All four protons are non-equivalent, and in that case, such type of splitting pattern is seen. For example, HA couples with HM, doublet is formed, but HA also couples with HP, therefore each line of doublet again split into doublets, therefore double doublet is obtained for HA. Similarly, for HX also we get the double doublet. For P and M type of protons, we get triplet of doublet. Because P type of proton couple with X and M, triplet is obtained, but it also couples with HA, therefore triplet of doublet is seen in the spectra. Similarly, for proton HM also we get the triplet of doublet, and the spectra is second order or non-first order. In that case, the para coupling is nearly zero. Therefore, para coupling is not considered. And such type of system is known as AMPX system. Then, system containing 5 interacting nuclei. First we see A2X3 system. A system containing two sets of protons, A and X, in which two magnetically equivalent protons coupled with other set of three equivalent protons which is far removed in chemical shift. Such systems are observed in compound containing ethyl group. HA type of protons gives quartet, while HX type proton gives triplet in the spectra. The spectra is first order. This is A2X3 system. The simple example is ethyl bromide. The CH2, as it is deshielded, it is designated as A. There are two protons, therefore it is A2. This is the X3 system. A type of proton gives quartet and X type of proton gives triplet in the spectra. This is A2X3 system. Then A2B3 system. This is also ethyl group of spin system, a system containing two set of protons in which two magnetically equivalent protons coupled with other set of three equivalent protons having nearer chemical shift value. Such systems are observed in compound containing ethyl group attached to less electronegative atom, and the spectra is second order. Let us see the example 1-bromohexane, and in case of 1-bromohexane, the ethyl group exhibits the A2B3 system, and as ethyl group is attached to a carbon atom, the chemical shift value of A and B are very nearer to each other, and therefore complex splitting pattern is seen in the spectra, and the spectra is non-first order or second order. This is A2B3 system. Then next system is ABX3 system, a system containing three sets of protons A, B and X. Two sets of protons having nearer chemical shift value, and it couples with third set of protons having well removed in chemical shift, and the spectra is second order. For example, 1-bromopropene. In case of 1-bromopropene, there are three sets of protons. Ha type of proton couples with methyl group protons, the quartet is obtained, but it also couples with Hb type of proton, therefore we get the signal quartet of doublet. For B type of proton also we get the quartet of doublet, and for methyl group proton, that is X3 type of proton, we get the doublet of doublet. It first couple with Ha, we get the doublet. It also couples with B, therefore each line of doublet again split into two lines, therefore we get the double doublet in the spectra. And the spectra is second order or non-first order. This is ABX3 system. The next system is AA-BB-C system. There are three sets of protons, but out of that AA- are chemically equivalent but magnetically non-equivalent. BB- also chemically equivalent, magnetically non-equivalent. And such type of systems are commonly seen in mono-substituted phenyl groups. Thus, spectra is a second order spectra. For example, this is the mono-substituted benzene. There are three sets of protons, Ha, Hb and Hc, but Ha and Ha- are chemically equivalent but magnetically non-equivalent. Similarly, BB- also chemically equivalent but magnetically non-equivalent, as their coupling constants are different. And in that case, AA- gives the double doublet. For B also, for B type of proton, we get the triplet, and for C type of proton, it gives triplet of triplet. Because C type of proton couple with B and B dash, we get the triplet. Now again it couples with A and A dash, therefore triplet of triplet is obtained. If R is electron withdrawing, then such type of scenario is seen. And if R is electron donating, then BB dash is a deshielded proton, C and then A dash. This is all about designation of nuclei in spin system, and we studied different type of spin systems in this video. And with the help of that Pople nomenclature, we can designate any type of spin system, and that spin system designation depends upon their chemical shift values and the difference in their coupling constants. Thanks a lot for watching this video. Thank you very much.